Hello everybody, and welcome to this video where we'll be talking about the ABL, atmospheric boundary layer, and the LCL, lifting condensation level, and how to see them in a Skew-T. My name is Brian Verhoeven. I'm a wildfire researcher at the Netherlands Institute for Public Safety, and I coordinate the fire analysis team in the Netherlands. In this session, we'll have two parts. First off, how to recognize the LCL and the ABL in a Skew-T diagram. And then the second part will be, okay, then how can we determine if a regular cloud formation, so cumulus cloud formation, is possible in the current state of the atmosphere. So let's talk about how to find the LCL, the lifting condensation level. And we're going to do so by just doing an example. For this example, in a Skew-T diagram in a slide, we'll take a temperature of 20 degrees Celsius at the surface, highlighted by the red circle in the diagram. Now we also need a dew point temperature at the surface, and in this case I've taken 5 degrees Celsius. And mind you, this is a hypothetical scenario, but it's pretty realistic. We can see those days. Now if we have a parcel and it starts to rise, and it's for whatever reason, because of a mountain, because of a weather front or something else, maybe it's just warmer than the environment. If the parcel starts to rise, we have to follow a line. And we've learned before that this is the dry adiabatic line. So let's do that in this example. And I've done this by following the green line. Now we want to know where the parcel becomes saturated. So it's cold enough and it cannot contain all of the moisture in a gas form, so we start to get condensation. To determine this point, we need the dew point temperature, and from that temperature at the surface, we start to follow the line of equal amount of absolute moisture. In this example, you can see it by following the purple line. These two lines, they cross, and that's the point where we find the LCL, the lifting condensation level. In this example, it's at about 800 hectopascals height. Now, from that point on, we need to follow the blue line, the moist adiabatic line. So if a parcel keeps on rising, but there's also condensation, and this condensation releases some heat, it still cools down, but a little bit less quickly because of the heat being released by condensation. So we need to follow the moist adiabatic line above 800 hectopascals in case a parcel would still rise. And nevertheless, we found the lifting condensation level here. So we know where we can expect cloud formation. How tall or how deep the cloud will become is very depending on how long the parcel can keep on rising. And this example, we don't have that there because we don't know the temperature the parcel will encounter when it keeps on rising. So we don't know the temperature of the atmosphere. But nevertheless, we found the lifting condensation level, and we can use that knowledge for the next parts. So for the next part, we need to know on how to find the top of the ABL. So how can we identify how high the atmospheric boundary layer is in a certain case? And to do this, I am taking an example here of a real-life Skew-T diagram. So this is a Skew-T diagram based on a weather balloon observation. Now, if we remember correctly, then the atmospheric boundary layer, at the top of it, you will find an inversion, so an increase in temperature. On some days this is very clear, and on some days it's pretty weak. Now if you take a look at the diagram, and maybe you've already seen it, we can find a very clear inversion, and it's just above 900 hectopascals level. Because at that point, the temperature of the atmosphere jumps to the right, meaning that the temperature increases, and thus it's the inversion, indicating the top of the atmospheric boundary layer. Now there's a second hint here, and it's a very clear example in this case, but there's a second hint that helps us to identify the ABL, or the ABL top. And that's the fact that there's much drier air just above the boundary layer. And we can see it there as well, because we're following the blue line, the dew point temperature, just above the 900 hectopascals, it jumps to the left, indicating a much drier air mass. And that's again another way to see and to find the atmospheric boundary layer top. So in this case, the boundary layer gets just above 900 hectopascals, so That's roughly estimated to 1300 meters height. And then we get into the free troposphere. So the purple line here is the ABL. And there's another one that we just talked about, the LCL. The LCL in this case is already highlighted in the diagram on the right-hand side of it, but it's just above the boundary layer. So can we expect a cloud in this case? Well, it's not easy because parcels of air rising in the boundary layer are generally not able to get just above it to reach the LCL. But it's not impossible. For example, because of the temperature that becomes a bit higher, or there's a little bit more moisture, or throughout the day, the boundary layer increases in height. And of course, in the context of these videos, there's also a possibility of a wildfire, but we'll be talking about that later on. So let's take another example on how to find the atmospheric boundary layer using a modeled Skew-T diagram. But we're going to take the same steps as before. And one of the first steps is to look for the inversion. If you look along with me and you look closely, we do not see the same strong step as in the previous slide, but we see the temperature increase starting from a level of about 740 hectopascals. From there, the temperature increases again, indicating the inversion. Now, there's another indication in this case, and it's again the amount of moisture. At this same height, we start to see the line of the dew point temperature move to the left, indicating drier air. And again, it's hinting us towards the fact that at that level is where the atmospheric boundary layer ends and we start to see the free troposphere. So, finding these two levels here, we have the ABL, and of course, we still have to find the LCL, the lifting condensation level. And maybe this is a moment for you to challenge yourself to find the lifting condensation level. So feel free to pause this video and take a look at the diagram and determine the LCL for yourself. Now, the nice thing in this diagram is that this is also done for us. So starting from the surface, we can see a red line following a dry adiabatic line. At a certain level, it switches to a different angle and it starts to follow the moist adiabatic line. That switching moment, if we remember, is where we find the LCL. So maybe you already found the same place, but the LCL in this case is located at about 640 hectopascals, 650, 640. And I hope you find the same. Now the final question is, if we have a parcel and it rises from the surface, do we expect cloud formation? And I hope that your answer would be no in this case. Why? Because the LCL is far above the boundary layer. So if a parcel of air would rise higher and higher because it's warmer than the environment, it hits the top of the boundary layer, and because there the temperature increases, it starts to become colder than its environment and cannot keep rising. So it hits its head and it cannot keep rising. So no cumulus cloud formation is expected following this Skew-T diagram. So I have one more example for you on how to find the ABL in a different case. It's an example, again, using a model Skew-T diagram, but on a different time of day, and maybe you can make a guess. Let's find the inversion here. So let's find a moment where the temperature starts to increase. And if you look at the Skew-T diagram, we can see that the temperature increases from the surface going up basically straight away. So the inversion here is indeed near or at the surface practically. And that means that we have a different type of atmospheric boundary layer than we've seen before, namely the nocturnal boundary layer. So this is a boundary layer example at night, where there's a strong inversion close to the surface. Do we expect cumulus formation because a parcel can rise as long as it's warmer than its environment? No, because when it starts to rise, practically straight away, it becomes colder than its environment, meaning that it cannot rise by itself. So this is an example of a nocturnal boundary layer with an inversion very close to the surface. And now it's time for an exercise for you all. I have an example of an observed, so a weather balloon or radiosonde Skew-T diagram. And my question to you in this case is, do you expect the formation of cumulus clouds in a case where a parcel can keep on rising by itself? So there's no forcing by a mountain or whatever. This case is from the build in the Netherlands, so as you can imagine, it's flat. Now, pause the video, take a look at the diagram, maybe take a screenshot and, for example, use PowerPoint to throw in some lines and follow the path of a parcel rising from the surface. But at least pause the video, do the exercise, and I will tell you the answer in a second. Now, I hope that you've taken a pause and done the exercise, so let's talk about the answer. In this case, we find the LCL at about the level indicated in the diagram. And there's a very clear indication in the diagram by itself as well. So in the observation, probably the weather balloon has gone through a cumulus cloud. Why? Because at that level, at the same level of the LCL, we find that the temperature and the dew point temperature of the atmosphere at that level, so not of a parcel, but of the atmosphere at that level, they are touching, meaning a relative humidity of 100%. So there was a cloud there. Now we can confirm in this diagram the LCL level as well, because the red circle there shows the LCLP, so the pressure level of the LCL, which is almost at 780 hectopascals in the example. So do we expect cloud formation here? The answer is yes. So, in summary for this session, we can now often recognize the atmospheric boundary layer using a Skew-T diagram. We've done this by two indicators, finding the inversion and maybe also finding a change in the dryness or the amount of moisture in a certain layer. So sometimes there was an indicator where the atmosphere became way drier just above the boundary layer. We can also analyze if a rising parcel from the surface is able to reach the lifting condensation level, the LCL. And if it's able to, we can expect cloud formation or cumulus cloud formation. So if the answer is yes, we expect cumulus clouds. If the answer is no, maybe we expect clear skies or clouds at a different level, of course. In the next video, we'll talk about how to analyze the possible effect of a wildfire in a Skew-T diagram. So I hope to see you in the next video, and thank you for watching this one.